Now, moving on from our chapter in relation to chemical equilibrium, we're going to move into something which is a little bit related to the Kc expression that we were dealing with in the previous chapter. I do need you to remember how to build your Kc expression. Just keep that in mind. It's the concentrations of the products divided by the concentration of the reactants, and they're all raised to the power of their respective coefficients. Okay, that's going to come up again just in order to develop a formula that we're going to use in terms of pH of different acids and bases and so on. So, as we should already know, pH is nothing more than a measure of the strength of an acid or a base. Okay, it's a measure of the strength of an acid or a base. And from an earlier chapter, we discovered that the strength of an acid is totally dependent on its ability to produce H plus ions in solution. That's the Arrhenius theory. Or, if we want to talk about Bronsted-Lowry, it's the ability of an acid to donate protons. And the better the proton donor, the stronger the acid and so on. Okay? But the letters pH themselves, they stand for, if you notice the way they're written, it's written with a small p and a big H. So it actually means the power of hydrogen. Okay, the power of hydrogen. So therefore, our interest in this section is going to be the H plus ion. That's going to be our interest. Now, yes, even when it comes to bases, I know we said that bases are substances that produce OH minuses in solution. That's the narrow Arrhenius definition. But if you put OH minus into water, what it simply does is affect the balance of H plus in the water. Okay, so it still goes back to H plus, which I'll show you in a few moments. So water itself, there's a myth out there that water is a great conductor of electricity. Okay, that if you drop something electrical into water, it'll carry a current. Yes, providing that the water has ions. So if you have water that is distilled, pure water, what we will notice is that it carries a very, very tiny charge. Now, charges can only be carried if there are ions present in the water. So because pure water can conduct a very, very small electrical current, or a tiny current, that means that there must be a tiny amount of ions present in water. And in fact, the only ions that can be present in pure water, distilled water and deionized water, are the ions that are made when a water molecule itself just automatically breaks up into H plus and OH minus. Okay, now that does happen. Mind you, it only happens perhaps to one molecule in every 500 million. So it's a very, very tiny amount we're talking about here. However, it is small enough in order to allow a tiny current to pass through pure water. But what I want you to notice is this, that water, because the dissociation is automatic, builds up an equilibrium with its own ions. So therefore, straight away, we can talk about a Kc expression as being the concentration of hydrogen over the concentration of the hydroxide ions divided by the concentration of water itself. Now, concentration of water has got a concentration. We talk about that later on. It's a constant, okay? At different temperatures, it has a different value, but it's a constant value at that particular temperature, and we'll talk about that later. So that's what I want you to just think on in terms of the previous chapter, that if water is able to set up an equilibrium with its own ions produced by dissociation, well then there exists a Kc which is calculated by multiplying the concentrations of H plus and OH minus ions together and dividing it by the concentration of the original water. Now, here's one thing I want you to remember. One molecule breaks up into one H plus and one OH minus. 2 would break into 2 and 2. 20 would break into 20 and 20. A million would break into a million and a million. So therefore, what I'm trying to tell you is this. The numbers of H plus ions and OH minus ions that are produced are always going to be the same. They'll be equal. And if you have an equal number of H plus and OH minus ions, that's the reason why we describe water as being neutral. Because there's no excess of plus or there's no excess of minus. They are perfectly equal in concentration. And because the plus concentration is the same as the minus concentration, they simply cancel to give you what we call a neutral liquid that we know has a pH of 7. Now, I'm going to try and link all of this back to the pH of 7 in a few moments, but that's what I want you to think of in terms of the previous chapter. Okay, in order for a current to flow, as we said already, ions must be present. But if the water is pure, what are the ions? And the answer is the the automatic dissociation of water into its own H plus and OH minus ions. And as we said already, it's about 1 in every 500 million water molecules that will automatically dissociate. Now, it's a natural process, okay, as shown in this diagram here. Now, notice, and if you can think back to the time we were talking about acids and bases, roughly this time in 5th year, we spoke about the fact that when water dissociates into H plus and OH minus, the H plus is actually carried by another water molecule. So there's no such thing really as a H plus. It piggybacks on a H2O to become H3O, which is the hydronium ion. That's only a technicality. We don't really need to remember that here. So just keep in mind that one water molecule breaks up into one OH and one H plus. Since H plus cannot exist on its own, as we said already, it is more correct to show the dissociation of water as the following. And this is something we spoke about in 5th year. Two water molecules. Notice that this hydrogen breaks off, becomes H plus, but because protons can't exist on their own, it piggybacks on the water molecule to give you H and O and H plus. And overall, because water is neutral, that is the hydronium ion, which can be treated as a symbol H plus. Okay. The automatic dissociation of water is known as self-ionization. Now just watch for that term. Anything again in red is extremely important. But self-ionization is the automatic process whereby a substance breaks up into its constituent ions. And in this case here, water breaks up into H plus and OH minus. And I'm asking a question here just to make sure you were listening earlier on. Can we explain why water is pH neutral? And the answer is yes. Because if water dissociates into its ions, the ions are H plus and OH minus. That means an equal number of both are being formed. And they'll simply cancel one another in order to give you pH neutral. Okay. The dissociation of water is expressed as, now we've had this already, the water molecule existing in equilibrium with its own ions. And therefore the Kc expression is simply nothing more than the concentration of H plus by the concentration of OH minus over the concentration of H2O, something that you should be able to write yourself. Now, here's what I want you to think of carefully. We've already said that the concentration of H plus is equal to the concentration of OH minus ions in water. The same concentration of both are produced. So therefore, both of these concentrations will be the same number. So what we can say in shorthand is that really we are multiplying the concentration of hydrogen ions and squaring it. In other words, we're multiplying it by itself being also the concentration of OH minus. I hope that makes sense. So H2O gives a H plus and an OH minus. Okay, the numbers of H plus and OH minus are the same. So therefore, if you're multiplying the concentration of H plus by the concentration of OH minus, and they're both the same number, the shorthand way to write it is H plus to be squared, the concentration of hydrogen ions to be squared. And the reason why I want to do that is because I now want to clear the fraction, okay? And if I clear the fraction, all I've got to do is multiply both sides by the concentration of H2O in order to end up with this equation. And this is extremely important, all right? Because Kc is a constant. We already know that. It's the equilibrium constant from the previous chapter. The concentration of water at different temperatures is also a constant value. So therefore, these two here are actually two constants. And because they are two constants, when you multiply two constants together, you get a constant. Okay? So what we can say here is we can blend Kc with the concentration of H2O into a new phrase called Kw, which is, as we call it already, the ionic product of water. It's the value that's formed when the two ions, or the concentration of both ions, H plus and OH minus, are multiplied by one another. But because H plus and OH minus are the same, we end up getting H plus squared. So you're going to see in the next slide, I'm going to replace these two here by Kw. Apologies for that. Kw. Okay. So since Kc and H2O are both constants, so the concentration of water is constant at any given temperature, and Kc is an equilibrium constant, so these two are both constants. And if you multiply two constants by one another, you get a new constant, and that new constant is, as I've had down here on the slide, Kw. Okay, so Kw is known as the ionic product of water, for the very simple reason that you're multiplying the concentration of H plus by the concentration of OH minus. But because they're both the same, we could say, look, the concentration of OH minus is exactly the same as the concentration of H plus. So therefore, we can write the ionic product of water as H plus to be squared. And it has a value of 1 by 10 to the minus 14 at 25 degrees. Now remember I told you Kw is temperature sensitive. We said this in the previous chapter. All equilibrium constants and all their derivatives are extremely sensitive to changes in temperature. The value of all Ks, be it Kc or Kw, changes at different temperatures. So in this case here, you'll notice that it's 1 by 10 to the power of minus 14 at 25 degrees, but it is 51.3 by 10 to the minus 14 at 100. Now what that means is the more energy in the system, the more dissociation you're going to have. Okay. In fact, you'll have 51.3 times more dissociation in hot water than you will in 25 degree water because of the energy content. The more energy you give something, the more able the water molecules are to break into their constituent ions. So there's an example. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 water molecules, amongst which one has popped into H plus and OH minus. Okay, so that's just to show you that one H2O can break up into a H plus and an OH minus, meaning that the concentration of these two will always be the same. That's why we can write them down as H plus to be squared. Now, H plus to be squared at 25 degrees, we've told you already, is 1 by 10 to the minus 14. Okay, what would happen if I was to just clear the square? Or how do I clear a square? Well, the answer is get the square root of both sides. And if I get the square root of both sides, I get the hydrogen ion concentration of water to be the square root of 1 by 10 to the power of minus 14. Now, if you do that on your calculator, you come out with something very interesting. And I hope people remember another way to write a square root is the power of a half. And a half of minus 14 is minus 7. So the concentration of hydrogen ions in pure water at 25 degrees is 1 by 10 to the power of minus 7. Now, here's a question. What's the pH of neutral water? The answer is 7. So there must be some connection between the hydrogen ion concentration of pure water at 25 degrees and the pH of that water. We can see it already beginning to appear, 1 by 10 to the minus 7. Now, how do I get that into a pH of 7? And that's really what we want to look at. I wouldn't be too concerned with the theory that's just gone past. I'd like you to understand it in order to get an idea of where I'm getting this from. This is very important. We've got to know where that comes from. You won't be examined on how to derive that, but I do want you to know how I get it. And here's how I get it. Listen again very carefully. Water dissociates into H plus and OH minus. Okay, so therefore, in essence, water gives the same concentration of H plus and OH minus when it dissociates. Okay, when you multiply the H plus by the OH minus, you get 1 by 10 to the power of minus 14 as the ionic product. But because H plus and OH minus are both the same concentration, then 1 by 10 to the power of minus 14 can be represented by H plus to be squared. You get the square root of both sides and you end up with the ionic product of water breaking down to tell you that the concentration of hydrogen ions is 1 by 10 to the minus 7 in pure water at 25 degrees. Okay, now here's the important thing. Kw is a constant. That's the Kw comes from, don't forget, Kc multiplied by H2O. Okay, just remember that, which is, as we said already, H plus by OH minus, which again we said was the same as H plus to be squared. Okay, and that's 1 by 10 to the power of minus 14. When hydrogen ions change, now from this, don't forget, we've already ended up with H plus squared is equal to 1 by 10 to the power of minus 14, meaning that just H plus on its own, the concentration of hydrogen ions, is 1 by 10 to the power of minus 7. All right, but I just want to go back here for a moment and I just want to look at this to see where it actually comes from. Let me just take this out here for a moment and let's just go back to what I said over here. This part. So that's important. That Kc times H2O is H plus by OH minus, which is 1 by 10 to the power of minus 14. Now, here's the important thing. Let me just write that here. H plus by OH minus equals 10 to the minus 14, or 1 by 10 to the minus 14. Look, what happens when you multiply anything by 1? It stays the same. So let me just deal with 10 to the 14 for a moment. Don't need to multiply it by 1. Okay, that's when they're balanced, all right? But let's say, for example, that I now increase the hydrogen ion concentration up to 10 to the minus 9. Isn't it very easy to see that 10 to the minus 14, that value is kept by this one here going up to minus 9 and minus 5. Okay, so you're noticing, and again, if I brought this down 10 to the minus 2, this one here would be OH to the minus 12. In other words, the powers over the hydrogen and the hydroxyl ions always have to add to minus 14. So in other words, as you can see from this one, as we change the concentration of H plus or OH minus, we make the resulting solution more or less acidic. Okay, that's extremely important. So here, the highest value between these two is this one. So therefore, there are more H plus ions than OH, so this would be acidic. Take a look at these two. The higher value now is 10 to the minus 5. So therefore, this one will be more in excess than this one here, so you end up getting a basic solution. So in other words, when you have minus 7 for the H plus and minus 7 for the OH minus, they'll give you minus 14, but they're equal, so it's neutral. If you change one number, the other number, the power over the 10, will have to change in order to keep the total of the two powers at minus 14. Okay, so it now becomes a very simple exercise. Let's look at it again. If H plus equals 10 to the minus 5, then the concentration of OH minus must be 10 to the minus 9. Why? Because the two powers over the 10s representing the concentration of both ions have to add to 14. You can't get away from that 10 to the minus 14. And likewise, if I was to drop the hydrogen ion concentration down to 10 to the minus 8, which is very small, then the OH minus ion concentration will be 10 to the minus 6, because again the powers have to add to minus 14. But here's what I want you to notice. When there's an imbalance in the powers, the highest one wins. The highest concentration wins. In this case, 10 to the minus 5 is a larger number than 10 to the minus 9, so this one will be acidic. In this one, 10 to the minus 6 is a larger number than 10 to the minus 8, so this one here would be a basic solution. So really, at the end of the day, when you multiply H plus by OH minus ions, you'll always get 10 to the minus 14. In water, at 25 degrees under normal conditions, the H plus concentration will be 10 to the minus 7. The OH minus ions will be 10 to the minus 7, giving you a neutral solution with a total combination ionic product of 10 to the minus 14. When you start to change the powers over the 10, you've got to change them in such a way that they still always add to minus 14. And then all you've got to do after that is choose the one that is the highest value, and that is the one that will give the overall basicity or acidity of that solution. So, the balance between H plus and OH minus reveals whether the solution is acidic or basic. So if your concentration of H plus is greater than OH minus, it'll be acidic. For example, if this is 10 to the minus 3, this one here will be 10 to the minus 11. Okay, don't need brackets in it, it's just an example. Okay, that's that one. Next one. If your OH minus is greater than your H plus, so let's say that this is 10 to the minus 1 and this is 10 to the minus 13, well then that's definitely going to be a basic solution. And when the two are equal, 10 to the minus 7 and 10 to the minus 7, you'll have a neutral solution. So therefore, acidity, basicity and neutrality are all got to do with the balance in the concentration of H plus and OH minus. Now, taking this into history, the very first person to become a little bit perplexed by all of this hydrogen ion concentration was a Danish guy called Sorensen. Okay, and believe it or believe it not, Sorensen experimented on beer. And he discovered very quickly that the pH of beer was 5. And also at the same time, having figured out that the pH of beer was equal to 5, he discovered that the hydrogen ion concentration was 0.00001 moles per litre. Okay, that's what it actually was, 0.00001 moles per litre. That was the hydrogen ion concentration. Now, mathematically, what's the link between these two? How did he get his hydrogen ion concentration up into a pH of 5? And the answer is he developed a formula. And he developed a formula that said that the pH of any solution is equal to minus the log of the hydrogen ion concentration. That's it. So in other words, if you knew the hydrogen ion concentration and you get minus the log of that hydrogen ion concentration, you'll get the pH. Now, if you test it on your calculator, if you put in on your calculator, now, by the way, the log I'm speaking about is the log that is in between, I don't know if you can see it there. It's the LOG button, this one here. See that LOG? That LOG, that's the button I'm talking about, okay? It's what we call the common log, or log to the base 10, as some people call it. But just log will do fine. So if I put in here minus, and I press the log, and I put in 0.00001 and close the brackets, hey presto, I get an answer, if you can see that, of 5. So now we've got a formula, and this formula is one of 2 formulas in this chapter. So there's only 2 formulas, that's it. This is the first one. That the pH of any solution is equal to minus the log of the hydrogen ion concentration. And please, on the calculator, remember that the button I'm talking about is the log button. It's just like that, okay? It just has 3 letters on it, L-O-G. Okay, so just to say, Danish chemist Sorensen introduced the idea of pH. He noted that beer had a 0.00001 moles per litre in concentration. And he called this a pH of 5. How? By using the following formula. And this is a formula you have to learn. That the pH of any solution is simply nothing more than minus the log of the hydrogen ion concentration. Now, one of the first things that will be examinable in everything we've done so far is this formula. Okay, not too worried about all the theory we've gone through so far. I do need to go through it with you in order to show you where we're getting this formula from and where we get the hydrogen ion concentration from. But this formula is of extreme importance because they will be asking you to calculate pH. Okay, so let's take an example. A solution has a concentration of 10 to the minus 4 moles of hydrogen ions per litre. What is the pH of this solution? Now look, every time you hear the word pH, will you simply please write down the formula? pH equals minus log of the hydrogen ion concentration. And then you scan the question for the hydrogen ion concentration. And there it is, a concentration of 10 to the minus 4. So therefore the pH will be minus the log of 10 to the minus 4. 10 to the minus 4. And you can put that on your calculator. So minus, and by the way, when I talk about minus again, it's the minus in the grey area, not the subtraction sign. That minus there beside my finger. Okay, so minus the log, minus log of 10 to the power of minus 4. And don't forget to close your brackets. And the answer comes out as pH equals 4. So the pH is directly related to minus the log of the hydrogen ion concentration. pH equals minus log of the hydrogen ion concentration, where H plus is in moles per litre. And please make sure it's in moles per litre. If they don't give you in moles per litre, you've got to change it first. That's what the square brackets mean. Second example. Calculate the pH of a solution whose hydrogen ion concentration is 7.1 by 10 to the minus 7 moles per litre. Again, when you hear the word pH, please write down the formula. Minus the log of the hydrogen ion concentration. Okay, which is minus the log of, now what is the concentration? The hydrogen ion concentration is 7.1 by 10 to the power of minus 7. Very simple. So again, minus the log of 7.1 by 10 to the power of minus 7. And that comes out as a pH of 6.148. So we'll say 6.15 is perfect. That's your pH value. Okay, relatively simple to use the formula, very, very straightforward. So again, I have it printed here. Minus log of hydrogen ion concentration, 7.1 by 10 to the minus 7, 6.15. Now, they won't stay as easy as that. They do change the questions a little bit to take into consideration that you've already studied how to deal with concentration and that you understand that square brackets of anything always mean moles per litre. So you've got to keep that in mind. Now, calculate the hydrogen ion concentration of a solution whose pH is 3.7. Doesn't matter. pH, write down the formula. pH equals minus the log of the hydrogen ion concentration. Now in this case, what do they give me? They want me to find the hydrogen ion concentration. So what I'm going to do here is replace the H plus with X, because I don't know what it is. And because they're telling me that the pH is 3.7, put that in here into the equation. So 3.7 equals minus the log of the hydrogen ion concentration, which at the moment is unknown. And all I have to do is first of all send the minus over here. So minus 3.7 is equal to the log of the unknown hydrogen ion concentration. Now, how do I get rid of the log? And the hint is there. You invert it. Second function log is something that will undo the action of a logarithm. Okay, so in this case, what I want to do now is I want to second function log with minus 3.7. So in other words, I'm going to get the inverse log on both sides. So when I get the inverse log over here, that just leaves me with x. When I get the inverse log over here, it's the second function log with minus 3.7. So shift log minus 3.7, and the hydrogen ion concentration comes out as 0.0000199. So do you know what? Let's just call that 2. And it'll always be in moles per litre. That's the hydrogen ion concentration. So you're just using the formula backwards. All right. So again, when you hear pH, write down the formula. Read the question and see what they give you. Here they've given me the pH of 3.7. So I put that underneath the pH. I do not know what the hydrogen ion concentration is, so I call it X. And then gradually I just break this side down to get X on its own. Send the minus over the other side and then invert the log with minus 3.7 by second function log on your calculator, and that gives you the answer. Now again, I have this typed out here for you, so you can work through it yourself. 3.7 is minus the log, minus 3.7 is the log. Now invert the log by using the second function log with the minus 3.7, and you end up getting, as we said already, 0.0001995, 0.0002 I said, or 2 by 10 to the power of minus 4. Okay, and finally then, calculate the pH of a 0.4 molar solution of HCl. Now that's when we've got to go back again and figure out, what does 0.4 molar mean? Well, before we do that, calculate the pH. Write down the formula. Minus the log of the hydrogen ion concentration. Now, be careful. They're not directly telling me the concentration of hydrogen ions. They're telling me the concentration of the entire acid. See that? So here's what I have to remember. When HCl breaks up, it breaks up into H plus and OH minus. In other words, one molecule gives one H plus. So you've got a ratio of 1:1, meaning that the concentration of the acid will be the same as the concentration of the H plus ions. So if this is 0.4 molar, this is going to be 0.4 moles per litre. And now I can put that hydrogen ion concentration in here and get minus the log of 0.4. And the answer to that, again, trusty calculator, minus the log of 0.4 comes out as 0.397. So 398, because it's 3979, so 398 will be fine. That's the pH. Be careful with the next one. Watch carefully. Calculate the pH. Again, pH equals minus the log of the hydrogen ion concentration. Now, is the hydrogen ion concentration given directly? No. In fact, we're now given the concentration of the acid. And the acid's concentration is 0.75 molar. watch what happens when it dissociates. Now, when it dissociates, we're going to get 2H plus and an SO4 2 minus. See that? So in other words, there is twice the amount of hydrogen in that molecule, meaning that the molarity is in a ratio of 1:2. So if 0.75 is the molarity of H2SO4, then twice that will be the molarity of the H plus, and that works out as 1.5 moles per litre. So now that I know the concentration of H plus, I carry it back into the formula, minus the log of 1.5, and minus the log of 1.5 comes out, sorry, minus the log of 1.5, did I do it right, 0.75 moles, yeah, hydrogen ion concentration, minus log of 1.5, or maybe I've gone too high, minus the log, sorry, minus log of 1.5, it's going to go into negative territory, yeah, that's fine, equals minus 0.176. I hear you say you got the wrong answer, you got minus. No. pHs, most acids exist between 0 and 14, but there are some acids whose pHs are blown above those values. Okay, so is it okay to get a negative pH? Absolutely. There's nothing saying that acids only have to have a pH between 0 and 14. Acids can have a pH of any value, but 95% of all my acids fall in that range. Some of them fall outside it, none that we work with, so therefore we don't usually have to worry about it. But there's your answer. So the pH of a 0.75 molar solution of H2SO4, that's the concentration of the acid. The acid is diprotic, okay, so it produces 2 protons per molecule. So if that is the concentration of the acid, then the concentration of hydrogen ions would be twice that, 1.5 moles per litre. So you carry that concentration of hydrogen ions back into the formula, get minus the log of it, and that's your pH. Okay, so now what I'm going to do is I'm going to stop there because I want you to practice that formula forwards and backwards. I'm going to ask you in this one here to do A to E. So you can pause it, I'm working it now, and then I'm going to ask you also to use the formula backwards, okay? Take the pHs that are given to you and then work back with the formula and put the minus over the other side and then undo the log by using the second function log, okay? And then we'll go on to the relationship between H plus and pH once we have mastered how to use that formula.